Now in the previous video we studied about electric potential and we came to a mathematical expression that electric potential will be equal to final potential at point B minus initial potential at point A, and it will be equal to work done divided by the charge which is creating the electric field. Now here there are 2 points. Now this particular expression VB minus VA, although we called it electric potential, but it is also called potential difference. It is a potential difference between the points B and points A. Okay. Now in this particular case that we studied, the point A is at infinity. It is very far away. Okay. So at infinity we take the potential equal to 0. So that means the potential at point A is equal to 0 because it is very far away from the electric field. It is not experiencing any force. So VA becomes equal to 0. So if we substitute here, then VB will be equal to W by Q. What if the point A wasn't outside? What if the point A was already inside and both points A and B were inside the electric field? Let us say this is point A where we have very small charge plus Q, and this is point B, and we need to bring, and here is this capital Q is here at the center, and we need to bring this plus Q from point A to point B. Same concept, it does not make any difference. The only thing changes here is that at infinity we took VA equals to 0, but here since A is not at infinity, it is inside the electric field, so there will be some value of VA. Then our original equation will stand. So this is our original equation, and we can change its terms according to the conditions, according to the given conditions. Here we are bringing plus Q charge towards B, so that means we have to do some work because we are moving against the force of repulsion. We have to do some work, so that work done will be equal to W, and the expression will be this. Now let us change the situation a little bit. Instead of plus Q, suppose we had minus Q charge. Now what will happen? Now if I ask you to bring this minus Q charge from point A to point B, do you actually have to do some work? Think about it carefully. This is a positive charge, this is a negative charge. This positive charge will attract this negative charge. So do I have to do some work in bringing this negative charge from point A to point B? It will come on its own. This charge will pull it on its own. I do not have to do any work. So that means in going from A to B, my work done will be equal to 0. Potential difference will be equal to 0. Potential is equal to 0 because I am not doing any work. But what if this minus Q charge was here, and this is your point A and this is your final point B, and you have to move this charge from point A to point B. Now do I have to do some work? Yes, now I have to do some work because this charge is pulling minus Q towards itself, but I am taking it away, so I have to do some work against the electrostatic force of attraction. This time it is attraction, earlier it was repulsion. Now I have to do some work against this attractive force. Again, this will be justified by the same formula. The formula does not change, only the values will change. Value you can put here accordingly, whatever is the condition. But the basic concept of electric potential remains the same. So I hope this is clear. Now what is remaining is the SI units. So SI unit of potential is volts, or we call voltage. You must have heard this word. So the SI unit is volts and it is denoted by capital V. The SI unit of work is joules, the SI unit of charge is coulomb. That means for this particular mathematical expression, volts will be equal to joules per coulomb. Remember this expression also. Sometimes the questions are tricky and you need to have this relation also.